Let us look at factorization, a very important concept. What this means is basically that given a magnitude AB and an area C, or in other words, another magnitude C, we have to find a point on AB, say S, such that AS times SB is equal to C. And actually, which also means that AS plus SB is equal to AB. So how do we find S? So let's see how we can find S. We take the midpoint of AB, and on EB we draw a square. Now let's mark these points as FG. Now from this square GB, we subtract GB minus C. So this square is GB minus C. Let's mark this point as P, O, and Q. Now we extend OQ to R, and we extend PQ to S, and we complete this parallelogram or rectangle ASQ up to here. Let's mark this as T. This is a square, and you will notice that this rectangle is equal to C. And what is this rectangle? What is the area of this rectangle? That is AS times SQ. But SQ is equal to SB because there is a square. So we can say the area of this rectangle is AS times SB, which is equal to C. And AS plus SB is equal to AB. So we have found two magnitudes, AS and SB, such that their sum is equal to AB and the product is equal to C. Now you might say, okay, what's so great about this? This is pretty straightforward, we can do it. But what if AB is not equal to 10? It is equal to 11. You notice we go into decimals. Factorization becomes that much more difficult. And somewhere in between, it's not a whole number. AB itself is a fraction, 9.387. And what if this is also not a whole number? That's the beauty of this geometric way of factorization. By the way, this is based on Euclid's Elements proposition 6.28. I will provide a link to this proposition in the description. There he is talking of more in general in terms of parallelograms, constructing parallelograms on AB. But what I have done is restricted myself to squares and rectangles. Very important concept. So that is factorization. Very interesting. Bye for now.